But mostly this is very important to know. I will reiterate this. You will see in all the places: LLD, HLDs, DSA, and many areas, right? How you store it depends upon how you wanted to access it, read, write, and based on that you choose the right data structure, and it would be useful in system design as well when you are choosing the different type of databases. In fact, it depends on that. When you are having append only database, Cassandra, you have a NoSQL database, MongoDB, you have a SQL database, MySQL, right? All these three databases have its own benefits that we wanted to know. And ultimately, all these databases has been designed considering these algorithm, keeping in mind how about the read and write. It all start with the in memory and then as a persistent layer. When you get a question right in interview about the design a system called e-commerce cart, right? Sometimes there's a blurred line between system design and the LLD. So how would you define that? Are you creating the LLD or are you creating the HLD? Because it can cover on both, right? You can create the classes, interfaces, method for the cart, you can store it, and you can design a system design as well, where you can create the client, API, databases, load balancer, and all that, right? So that depends upon mostly on in memory. If it is an in memory, right? The storage is in memory, then it's a part of LLD, where you're not thinking about a persistent layer, where you think about more about the data structure because it's in memory, where you will store in the hash map those orders. You will pick it from there. You if you wanted to go to the history page, right, you will have a list of all the orders that you wanted to keep it in the linked list or array list, right? uh, this is more about the LLD, right? Now it's the same problem if you think about the system design, right? Then you will not think about that. You will think about like which database you will store it, right? If you wanted to have like a faster retrieval, right, for your order history page, uh, faster retrieval, then maybe you think about the SQL database, where you can give the order ID and then you search it in a non-linear ways, and that's where you can display it, right? Now if you wanted to have display all the orders, you do not have such capability, then you do not want, because it's a log of n, right, for searching for it. Then you may think about kind of a append only database, not a SQL one, right? Maybe you think about the MongoDB NoSQL, where you'll just pull all those things and display it. You don't have to search one by one. So with that, you are able to connect the dots, right? How these data structures is being used. Arrays, array list, and linked list. Okay, what are the differences in these three? If you get a number, right, if you are creating a function, right, and in this function, let's say you're getting the int number, and you need to choose a data structure here. Which data structure out of these three? Maybe we can have any data structure, but to define our scope of the problem, let's say out of these three data structure you wanted to store, right? Which data structure you will choose here? Okay, so that depends upon which data structure will you choose here. That depends upon how you wanted to use it later on, how you wanted to access it. Okay, so for example, let's say here you have some numbers here, 1 5, that you, let's say that you have added into these array. Let's talk about the array first, right? So array is something that when you want to create int, right, int array, and then you need to say new int 10. So this array is of fixed size. That is the limitations of the array, and there is a beauty for that as well, right? So if array, right, in this array, in the memory, what we have seen, there are continuous memory allocation is already been defined, right? And there are the indexes for this. That's how you can access the any element from anywhere from the middle of this, right? And you can remove the element as well from this array, right? Adding and removing, maybe you can think about like we cannot like remove as such from the middle of this because the sizes are fixed. Maybe if you wanted to reset it to 0 or 1 2 3 4, that you can do at any point of time, read and update. But delete you cannot do it. So read and update, that you can do it very easily, but delete you cannot do it at all because the array is of fixed size. Let's say you have got another number here, right? You can't do anything of it. So array is very good It is a combination of all the data structure in terms, if you think about like kind of a hash map, where you can directly search for any number from the index, uh, arrays, linked lists, right? It can solve all the purposes. But the major drawback here is you cannot grow or shrink this. You cannot, like if you have millions of number, you cannot allocate an array with millions of memory allocation, continuous memory allocation, right? Forever. You cannot keep this memory. That's why you might have 5 elements at a time, you might have a million at a time. So that's why you cannot use array. And that's why the next data structure would be array list. So in this array list, when you define this array list, you define like, clear this, array list, and list is equals to new array list. I wanted to get into more on hands-on coding, but considering the time what we have, I wanted to cover the basic concepts of it. And in our next session, we cover the coding part of it, and where you will do a hands-on along with me to start, using the basic thing out of it. But let's cover the basic out of it, and we will have the time and space complexity as well for this. And we'll try to have our session close in next 30 to 45 minutes. Uh, but if you wanted to further extend, I'm happy to do it. And if you wanted to close a little earlier, please let me know. Okay.
Fine, sir.
So yeah, cool. Thanks. So let's say you have these numbers, right? 5, 8, 10, 12. So removing, first of all, it doesn't come into the array list, right? From here, these dynamic data structures start. You can think about these as a static data structure. These are the dynamic data structures being started. Now you can add, remove at any point of time. But how do you add and remove? That is more important, right? So in array list, now we are talking about the array list here. In array list, you can access any element based on the index as well. Okay, because this is very much close to array with some benefits. You can access based on, let's say this index is 0, 1, 2, right? So you can get based on the index, you can keep incrementing or decrementing, right? But here the problem comes, if you wanted to keep on adding, you can keep adding the numbers here, right? But the problem is when these arrays keep on growing, let's say you wanted to remove any element from in between, which was not possible in array. That's why we have the array list, right? But what would be the time complexity of removing these element from the array list? Okay, that is one what we need to see. And with the time complexity, we will touch upon with this example. Okay. So if you wanted to remove this, what would happen behind the scene in the array list? Maybe anyone wanted to talk about this?
If we
Okay.
remove, then it will like internally it is using array only. So if we remove, it will decrease the size of that array. Like it will create a new array of shorter length, and if that limit is crossed, depending on the capacity,
Yep, yep, that's correct. What would be the time complexity?
that would be O of n only.
Okay, why O of n? Because let's say you wanted to remove 10 from this array, you will have to search. For search, yes, the time complexity of O of n, because we don't know which element, right? The particular number is, right? So we search for 10, it's here, no, it's here, no, it's here, yes. So we got the number 10, that the time complexity of O of n, correct? That is for the read part of it. Now coming to the update, delete part of it. If you wanted to delete it, we can just delete it from the array, right? And array list provides a function to remove it from this particular index, right? Array list, we have, right? We created the list here. We can say list.remove, list.remove, and here it takes two argument, right? Two kind of different argument. One is it takes the number itself, and another is it takes the index. How we differentiate this, right? Basically, if we provide an integer data type to this argument, it consider that there is an index for it. If we provide the object to this based on that data type, it understand whether it is an index or it is a number. What my mean is, like, let's say you have a 10 element, and here also you have the 10 element as well, and this number is 17, and the index of this is 10, right? So when you say index list dot remove 10, right? And if let's say you don't know about this thing, which number it will remove? Would it remove this number or would remove the 17 for that index 10? So based
The-
on the data type, the 10 what
yeah.
you're providing it, right? Whether you're providing the 10 in this format or this format, and you can pass like do a typecast, right? If you're doing this, so that's how it will understand. Okay. Now coming to the time complexity. So these are by the way, these are the important concepts, right? Like you make a note of it, right? Whenever you go through it, this is how you define for list dot remove. The time complexity here is it has to remove right from this memory allocation. So why the time complexity is O of n, that we will touch upon now. As array list is a continuous memory allocation. Okay, it is, we can keep on adding it, but it stored into the continuous memory allocation, and that's where the index we are able to play around. That is something that you need to understand, that whenever you wanted to play around index, whichever data structure which takes an index to play around access the data, it is stored into the continuous memory allocation. So it is storing in the continuous memory allocation. It means if you remove this, then this space will be blank, right? And what happens is, if you remove this number, it does the left shifting of all the right side of element. So since you remove this here, right, it will shift 12 to this memory allocation, so that it would be the continuous memory allocation. 5, 10 we have, 12 it is shifted, so we have a 12, 15 it will shift, so that we have a 15, 17 shifted, then we have a 17, and then that extra memory allocation is here, and it's forever, right? So that's why at worst case, if you remove the 5 number, if you say list dot remove 5, right, it has to shift all the number, and when you shift each and every number, the time complexity is O of n. With that, we wanted to get into the next data structure, which is a linked list. But you see the benefit here, right? The benefit here is you are able to play around the index in array. You're able to play around the index here. When we talk about the linked list, we will not be able to play around the index. That the benefit we will lose here. But the benefit what we get here is the element we will be able to remove from the in between. Okay, so linked list here, if we create the linked list, right? So in the linked list, as we know, these numbers, right? These are the numbers stored, and that contains the address of the next node. So the number stored is 10, 20, 30, right? And let's say the address is 100 here, the address is 90, address is 80. And at any given point of time for the data structure, we only have access to one node at a time. So we have access to this head element. And now if you wanted to remove 20 from between, right, what we will say, we will just change the address. Instead of it pointing it to 90, this is a 90, we will point it to a 100. So this node is pointing to this, and this will be removed. In this case, right, for removing, the time complexity is constant. Searching, yeah, will be O of n in both the cases. But when we have access, we already have the access to the node, the time complexity O of 1, because it does not have to shift anything. So this is the beauty of the linked list. Continue with that, stack and queue. We already know, most of us, but let me touch upon that as well. The stack is something like this, right? Where if we have a requirement that we wanted to keep storing the number, and we only wanted to delete the last number, then only the stack is useful. But in case if you wanted to delete the number from in between, that you cannot do it in stack, and then that you have to use array list or the linked list. For example, you keep on storing 5, 15, 18, right? In your function, right? In your function, this function which we have taken an example, right? Which data structure will you use? That is the goal, right? For this function, we have used this. Now we're thinking about this, right? Now, if we have a requirement that we always wanted to have this data structure dynamic, we can store 10 number, 20 number, 1,000, millions of number, but we do not want to use an array list, right? We can use a normal array as well. to millions of storage, keeping it right and keep on adding it at the end, making a reference to this last index. Whenever you want, you can return the last index, what was the last added. We don't want that. Okay. Now array list is something, yes, we can use that, uh, removing it from the end, which is good. So now you see there is something kind of an overlap with the array list and the stack, because array list also be able to do it. And if you remove always the last element from the array list, you do not have to do any shifting. So removal of the last element would be always O of one time complexity. In fact, there is a one very beautiful algorithm, which is a hard level problem. We will come back to this at some point of time, where we are making use of array list and making its advantage that the last element removable is always of O of one time complexity. In that algorithm, this array list is used. And we are taking kind of a quick fix or workaround, right? Generally, we will say. But if you know the really the depth of it, you will be able to use it. And you will be able to justify to the interviewer as well. Removing an element, you say that it's a time complexity of O of n, but at the same time, when you are justifying your code, you are saying like I'm using array list, but I'm using it, removing it one last element, still the type complexity is O of one. How you will justify it? Why are you using array list? Why are you not using stack in that case? Because we wanted to take the advantage of the index. That's why we use array lists. I know I'm giving you a algorithm idea about that algorithm here, which you do not have the context, but I wanted to do the problem solving skills build on your in your mindset, that why we are understanding this and why these small things are very important. And some people I see, right, just going through the code for that algorithm, hitting the head, understanding, right, why we use array list, why we not use stack, and what is the time complexity we consider, why this is O of one, because we have not gone through that basics. That was the reason. Struggling, at later stage. Okay, coming back to this stack, right, we have a requirement, right, we wanted to keep on adding it these numbers, and whenever we want it, right, we can remove it. Using stack, we can use it, we can always grow our data structure, because the requirement was we wanted to ever growing data structure, always removing from the last element. That's why we use a stack. If you argue why can't we use array list, yes, we can use array list as well, but you need to justify, like removing the last element will be O of one. And uh, and when you start writing the code, you will feel that at some point of time, using array a stack for specific to this use case makes more handy, and justifying logically won't make sense for this array list. You will have to justify, but conceptually if you use stack, that will make more sense. Stack have operations like push, pop, or empty. I'm going little fast here. Okay, now you have a requirement for, like, you always wanted to remove, add, keep on adding. You need a, in your function, you want a data structure which is keep growing. Let's say you have added a 5, 7, 9, 20, 50, right? You keep on adding number. Fine, you can use. So far, right now we are thinking building our problem solving skills, right? Now we can use array list, now we can use linked list, now we can use stack here if you want, right? But then you got another requirement, that there is a requirement that we do not want to delete from in between. If you wanted to delete from in between, you will use linked list. But you need to see, like, how do you search it? Do you want to create a hash map, all that, right? Now there is a requirement, you can delete, you need to delete only the first element of this data structure. Optimization, right? This operation would be of O of one always. Okay, so now let's start thinking about which data structure you can use. Can we use array list here? Yeah, we can keep on adding with O of one, right? Let me say add with O of one, remove with O of one. Array list will be able to do this, but this removal is not possible, because we have seen in array list it's O of n time complexity, so we cannot use array list here. Can we use stack here? Yes, we can use stack here. So what we can do in stack, we can keep on adding 5, 7, 9, 20, 50, right? But we wanted to remove 5 from here. What we will do, we will create another stack, another data structure. We will keep on storing these number, right? And whenever we get the last number, like keep on removing this 50, 29, 7. Let's say 50, 29, 7. This will be the order. We take an empty stack here, and whenever we get the last number, whenever the stack is empty, let's say we have added the 5 as well, now the stack is empty here, right? Stack is empty, we have popped all the element. Now the top element we can delete it, and the remaining element we can add it, 7, 9, 20, 50. By the way, you can do all these exercise, right? That will help you to start, the coding part of it, understanding the more depth knowledge of these data structure. You should do this, right? Removing an element for this requirement using the stack, using the array list. This activity, maybe this is an activity which we are going through today. Considering the time complexity and the space complexity, here the space complexity is we are taking an extra stack here. And how much size of this stack? The size of this stack is almost all the element. It is depending upon the length of the storage. So that's why it is having the time complex space complexity of O of n. Time complexity is like once we are iterating through all these element 1n, and then again we are pushing it back to again 2n or 3n, right? When we calculate, how we calculate the space and time complexity, maybe I'll cover in the next session. But for now, you think about like we do not consider the constants. Like if it is 2n, 3n, 4n, you just consider the n. Why this is, maybe we'll discuss it later on. But the time complexity is O of n here. Right? Can we use the linked list here? Linked list, yes, linked list we can use it here because always we have access to the first element of the linked list, right? And always we can just do head equals to head dot next. Then my next head would be this. The next head would be this, right? So yes, linked list we can use, but also the right data structure for this is the queue. In the queue, it provides a method called offer poll, where you can offering, you can keep on adding whenever you say poll, right? It will just poll it from the first element. There you do not have to do the head equals to head dot next, delete head, right? Queue provide this functionality. That queue dot poll, it means it just remove the first element and then the first element would be here. So this would be your queue. Okay, so now you see that there is some similarity with linked list and queue, array list and stack, right? Array list you will have to do some operations, some indexing, play around. That you can do with stack directly with pop, push. Linked list also you need to do some operation, head dot next, next this, right? And then with the queue you can do it directly with, right? The time complexity and space complexity both will be O of 1 for adding it and removing it for the queue data structure. Okay, but also I want to touch upon this, right? There is some relation. So in fact, if you create a queue in Java, right, so you don't see there is a concrete class for the queue. There is an interface for the queue, but there is no class for the queue. So when you create, right, you will create it like this: queue something something, and then you will say queue equals to new linked list. This is how you create it. There is no concrete class in queue because it is actually implemented using the linked list. But why we are giving the name as queue? Conceptually defining it and providing the direct function, poll and offer. We are conceptually defining it with direct function, and it make more sense for the queue, like the first in first out, and whoever has added first in or first out, and then this is was last in last out. That's stack. This is the same case for the stack and linked list.